All right, as junior engineers, you've probably spent a lot of time with standard logic families, like TTL. But what happens when standard just isn't fast enough? Well, in the world of high-speed design, you need a different kind of tool. Today, we are diving deep into emitter-coupled logic, or ECL, a logic family built for one thing and one thing only: pure, uncompromising speed. So here's our game plan. First, we'll talk about why we even need something like ECL. Then, we're going to uncover its biggest secret, a little something called non-saturated logic. After that, we'll get our hands dirty and look inside the actual circuits, talk about the really critical engineering trade-offs, and even troubleshoot a real-world fault. And we'll wrap it all up with a head-to-head showdown with good old TTL. Okay, let's start at the very beginning. Why was ECL even invented? Well, the answer's pretty simple: the relentless, never-ending quest for more speed. Look, in things like high-frequency communications, supercomputers, you name it, the speed of your logic gates becomes the ultimate bottleneck. Your standard logic families, they just can't keep up. And this performance gap is the exact problem that emitter-coupled logic was designed to solve. So, what's the magic behind ECL's incredible speed? What's the secret sauce? Let's peel back the layers and look at the core concept that makes all of this possible. Here it is, the core secret. In a standard logic family like TTL, when a transistor is fully on, it gets completely saturated with charge. Now, to switch it off, you have to wait for all that stored charge to clear out. That delay has a name: storage delay. And honestly, it's the main reason other logic is slower. ECL is engineered from the ground up to prevent its transistors from ever getting into that saturated state in the first place. And this, right here, illustrates the difference perfectly. Think of it like a light switch. A saturated TTL switch has a tiny but measurable delay after you flip it. An ECL switch, because it avoids that deep saturation, feels almost instantaneous. It's getting rid of that storage time that gives ECL its signature speed. Okay, so enough with the theory. Let's see how this stuff is actually put into practice. We're going to jump right into the circuits that make ECL tick. On the left, we've got a basic ECL OR gate circuit, and you can see its truth table right next to it. Now, the very first thing that should jump out at you is that negative supply voltage, VE. That's a classic hallmark of ECL. At its heart, this circuit is really a differential amplifier. You've got the input transistors Q1 and Q2, and they're basically being compared against a reference transistor Q3. Let's trace the logic here. Let's say input A is low and input B is high. That high input at B, which is about negative 0.9 volts, turns on its transistor, Q2. This raises the voltage at the shared emitter point for Q1, Q2, and Q3. Now, since the base of our reference transistor, Q3, is held at a fixed negative 1.3 volts, that higher emitter voltage is enough to turn Q3 off. With Q3 off, the current gets redirected, or steered, over to the base of the output transistor Q4. That turns Q4 on and pulls our output high. This current steering is the key. It is way, way faster than fully saturating and cutting off a transistor like you do in TTL. Now, here's something that's really clever about ECL. You can actually configure it to give you both an R and a NOR output from the exact same gate. Check it out. If you take one output from the emitter follower, Q4, you get your R function. But if you take another output from the collector of that differential pair, you get the inverted NOR function. That is incredibly efficient for circuit design. It saves you space, it saves you power, it's just plain smart. All right, you know this was coming. As engineers, we know there's no such thing as a free lunch. ECL's blazing speed comes at a price, and it is our job to understand what those trade-offs are. And here they are. ECL circuits are power hogs. They can't drive a lot of other gates. That's what we call low fan-out. And those negative voltage levels mean they don't play nice with other logic families. But the biggest problem, the one that's going to cause you the most headaches in a real-world design, is its really poor noise margin. Let's put a number on that to see what we're dealing with. The entire logic swing, the difference between a high and a low, is just 0.8 volts. That's it. A tiny little bit of electrical noise, which you're going to have in any real circuit, can be enough to accidentally flip a 0 to a 1 or a 1 to a 0. This makes designing reliable circuits with ECL a real challenge. And yeah, let's not forget that negative power supply. When you're working with ECL, your ground reference at 0 volts is actually the most positive point in the whole circuit. If you're used to TTL, that is completely backwards, and trust me, it can make probing and troubleshooting incredibly confusing until you really get your head wrapped around it. Okay, let's switch gears from theory to practice. We're going to do a little troubleshooting. This is where your real understanding of the circuit gets put to the test. And this example, by the way, is actually based on a question from a past university exam. So picture this. You're at the bench, you've got this circuit in front of you, but someone made a critical mistake. The reference voltage for that first OR gate, it got connected backwards. So instead of negative 1.3 volts at the base of Q3, you're now seeing a positive 1.3 volts. The big question is, what does this do to our logic function? Let's break it down. The base of Q3 is now clamped at a high positive voltage, plus 1.3 volts. Meanwhile, our inputs, A and B, are switching between negative 0.9 and negative 1.7 volts. What does that mean? It means the base of Q3 will always be at a much, much higher voltage than its emitter. There's no way around it, and that forces the transistor Q3 into a permanently on state no matter what the inputs are doing.
And a permanently on Q3 creates a domino effect. It's always going to be drawing current, which pulls the voltage at the base of Q4 low, and that keeps the output transistor Q4 permanently off. The result? Our OR gate isn't an OR gate anymore. Its output is just stuck at logic 0 all the time.
So the consequence for the whole circuit is pretty significant. The intended function was to NOR input C with the output of the A plus B OR gate. But now, with that first gate stuck at a constant logic 0, the A and B inputs do absolutely nothing. They're totally irrelevant. The entire circuit's function just collapses to simply inverting input C. And this is a huge lesson. A single, simple component failure can silently and fundamentally change a circuit's entire behavior. So let's put it all together in one final comparison. As a designer, when would you actually make the choice to use the fast but frankly difficult ECL over the more common and robust TTL? This table really says it all, doesn't it? The bottom line is this: you choose ECL for one reason and one reason only, when speed is the absolute, non-negotiable #1 priority. You are making a conscious choice to trade away power efficiency, noise immunity, and ease of use, all for that extra performance boost. And that's our deep dive into emitter-coupled logic. It's a perfect case study in engineering trade-offs. It's a reminder that for every single gain in performance, there's a price to be paid somewhere else. So the final question I'll leave you to think about is this: as modern technologies keep getting faster and faster, is there still a place for a specialized, high-maintenance logic family like ECL?